So we looked at the discharge and whether that's just necessary for El Nino, or is it also sufficient? You always want to think about necessary conditions and sufficient conditions, because when you have a complicated system like El Nino, which looks different every time, evolves differently, and has different impacts, you definitely want to understand the full theoretical background, process understanding, predictive understanding, so that ultimately the goal is predictions, right? So we left it saying there must be some stochastic forcing involved in El Ninos, because discharge alone doesn't seem to be sufficient. There are years where El Ninos begin to evolve and then they disappear or they die away. Some people use the word aborted El Nino, but knowing what El Nino stands for, we don't want to probably use that. But anyways, without getting into controversial statements, this paper is on the strong influence of westerly windbursts on El Nino diversity. Despite the tremendous progress in the theory, observations, and predictions of El Nino over the past 3 decades, the classification of El Nino diversity and the genesis of such diversity are still debated. Diversity is basically the various patterns of warming that we see. We talked about Eastern Pacific El Nino, Central Pacific El Nino. There's also extreme El Nino. And this paper actually does clustering to show the patterns. Every time I start to talk, I get a frog in my throat. This uncertainty renders El Nino prediction a continuously challenging task, as manifested by the absence of the large warm event in 2014 that was expected by many. We propose a unified perspectives on El Nino diversity as well as its causes, and support our view with a fuzzy clustering analysis and model experiments. Specifically, the interannual variability of sea surface temperatures in the tropical Pacific Ocean can generally be classified into 3 warm patterns and 1 cold pattern, which together constitute a canonical El Nino, La Nina, and its different flavors. We just looked at a paper that said the position of the La Nina peak determines its impact on the Indian Ocean and the negative Indian Ocean dipole, and this paper argues there is only one pattern of La Nina, so obviously you know that the story is never complete. So although the genesis of the canonical cycle can be readily explained by classic theories, we suggest that the asymmetry, irregularity, and extremes of El Nino result from westerly windbursts, a type of state-dependent atmospheric perturbation in the equatorial Pacific. So it starts as synoptic events, basically noise, and then it can become part of the system, what we call multiplicative noise, as we will see. We already mentioned it a few times. Westerly windbursts strongly affect El Nino, but not La Nina because of their unidirectional nature. We conclude that properly accounting for the interplay between the canonical cycle and westerly windbursts may improve El Nino prediction. May improve, right? The question is always whether you are using a statistical model, whether you are using a simple model as we do in this paper a little bit later on, or if your full model is able to capture the synoptic events like the westerly windbursts. All these are critical for actual successful El Nino prediction, right? So here are the clusters. El Nino cluster 1 is clearly the cold tongue El Nino, but is much stronger on the eastern end of it. El Nino cluster 2 is more shifted towards the dateline, what we would call Central Pacific El Nino or dateline El Nino, and often it's associated with cooler temperatures here. And El Nino cluster 3, which is the classic canonical El Nino or the cold tongue El Nino, which extends from the coastline towards the dateline. And La Nina clusters basically 1, 2, and 3. Argument is that they are not statistically different, but you can can convince yourself that maybe the spatial loading is slightly shifted, which is what we saw in the La Nina and IOD paper. So here we are looking at evolution of observed SST anomalies and westerly wind bursts along the equator from January 1961 to December 2010. So we are starting in 1961 here. You can see the La Ninas and the El Ninos, the extreme El Nino, especially 82, 83, 97, 98, and so on, and strong La Ninas as well. And the green line here shows the thick green curve is the 28.5 degree C SST isotherm, which is the eastern edge of the warm salty pool as opposed to the cold tongue saline cold tongue on the other side. Warm fresh pool on the west and cold saline pool on the east. And these black lines here, which you probably cannot see here, it's more obvious than here. Here you can see them crossing into the eastern Pacific beyond the date line, a little bit here as well, much more so here in 97, 98, and also in 92, 93, and so on. These are the westerly wind bursts, and the main point is really that pretty much all El Niños have some westerly wind bursts associated with them. But there are also years when there are westerly wind bursts in the far west maybe that are not associated with El Niños. So obviously it begins to tell you that westerly wind bursts may be an essential part of El Niño, but there are years when they do occur, but maybe the system is not ready to generate an El Niño out of it, which means there may be a necessary condition, and westerly wind bursts may be the sufficient condition, or at least for determining the strength and pattern of warming, i.e. the El Nino diversity. Okay, so a simple Kane-Zibiak model is taken here, and a model of the westerly wind burst is put on it to compare the base model. It's an anomaly model, very simple model. It has wind response, wind anomaly response to sea surface temperature anomalies and gradients, but doesn't have westerly wind burst. But westerly wind burst models do exist because even the full models sometimes don't do them. So the model without the westerly wind bursts produces El Ninos and La Ninas, which are basically Eastern Pacific type and maybe strong and weak, but essentially it has a fairly regular, it depends on how long the run is, and there are other details about the reformulation of the same model by Battisti and Hurst, arguing that there was a little bug, let's say, in the code that makes the Kane-Zibiak model oscillate a bit irregularly. But if you fix that bug, then it doesn't. Then the oscillations become very periodic, and the patterns are, the El Ninos are not divergent. Their diversity is not there. By adding the westerly wind burst, basically this simulation, which goes from year 101 to 176, shows that the westerly wind bursts always start in the western Pacific. They don't have an effect on La Nina, but they can produce weak El Ninos and strong El Ninos, and maybe multi-year El Ninos and extreme El Ninos, cold tongue El Ninos, and even some Central Pacific El Ninos, and so on. So you can see the warming happening away from the coast are considered Central Pacific El Ninos, and the argument is that westerly wind bursts are essential, critical, important for producing various flavors of El Nino. There is a whole debate about whether the diversity of El Nino is just in the same spectrum, and it's just not independent modes of variability, which pretty much everybody considers to be the case in terms of just the spectrum is spread out, so you get different flavors. Okay, the paper also looks at the dominant terms in terms of zonal advection, meridional advection, vertical processes, and the damping term and the SST warming DT/DT. And you can see that in the extreme El Nino cases of cluster 1, the vertical processes dominate, vertical advection, so thermocline Biekness feedback essentially is very strong. Wind anomalies are, westerlies. Thermocline is deeper, divergence is weaker, upwelling is weaker, gradient feedback to the thermocline and mixed layer processes and El Nino are stronger in the extreme El Nino, whereas in cluster 2 you can see none of the terms really dominate, whereas in the cold tongue El Nino, meridional and damping term is there, but its dependence is a bit complicated. But you want to look for dynamic processes, which are the advection and horizontal and vertical advection terms. So here you have contributions from all advection terms, and for La Nina, you have also contributions from all advection terms. Okay, so I'm being brief, but essentially this model, this paper argues that westerly windbursts are very much a part of the El Nino diversity and are essentially a necessary condition for El Ninos. All El Ninos have westerly windbursts. Wind measures here looking at January, February, March, April, May, June, for the various El Ninos, and you can see 97-98 had a very strong wind measure in March-April, whereas 82-83 had spread out, started in January-February, and weak events in March-April and May-June, whereas 86 had a late burst, 91 had weaker, but March-April dominated 97, but so did May-June. Basically, the extension into May, June, and beyond can also indicate that the noise or the westerly windbursts are pushing the warm pool eastward beyond the dateline, and they are becoming larger in fetch and strength, so they have become multiplicative noise, which means they are now part of the coupled system. They are not just stochastic forcing. Okay, so these are the terms here in warm water volume is a measure of the equatorial heat content presented by warm water volume above the 20 degrees C isotherms, which we have discussed before. These variables are integrated over the equatorial Pacific, so 5 north, 5 south, east to west, based on the reanalysis products, 2 of them. Blue, green, and brown bars denote mean values for January, February, March, April, May, June, and you can see how the warm water volume was changing. So you can see here for 97-98, again, there is a correspondence with the westerly windbursts. So heat content is building up as the warm pool is moving eastward. Thermocline is deepening and flattening, and you are producing high heat content near the surface above the 20 degrees C isotherm. Weaker ones have weaker evolution of the zonal spread of the warm water. Okay, so in summary, the analysis presented here support the notion that El Nino is likely to be a result of the interplay between a self-sustaining symmetric oscillation dictated by classic theories, so it's very much a stable oscillator, and the WWB type perturbations that are partially modulated by El Nino itself. That's what makes them multiplicative noise. The former provides a basic dynamical framework, whereas the latter gives rise to different flavors of El Nino. Such a scenario is appealing because it reconciles hotly debated issues related to the classification and genesis of various El Nino events by killing 3 birds: diversity, asymmetry, and extremes with one stone. So El Nino, La Nina diversity, El Nino diversity, El Nino, La Nina asymmetry, and extremes. Strong El Ninos along the coast, like 2026 is evolving to be. But one must not dwell on the simplicity of the picture painted here. Our intention is to emphasize the strong influence of WWBs on El Nino diversity, but not to downplay other processes that may play significant roles in El Nino dynamics and thus contribute to the complexity of its diversity. For example, there are other precursors from both the northern and southern Pacific extratropics that seem to be important triggers in the excitation of El Nino events, the Pacific meridional mode being the dominant one from the North Pacific, but also from the South Pacific. It's argued to be South Pacific meridional mode doing similar things. Moreover, aside from westerly windbursts, there are also easterly wind surges in the equatorial Pacific which may excite cold events. The relative importance of all these processes and the possible interactions among them should be further explored to achieve a comprehensive understanding of El Nino diversity. And immediately you understand that the problem with models is that if full models don't do this explicitly, then we cannot really analyze this. So we have to wait for models to get high enough resolution maybe to resolve WWBs explicitly and then make the flavors of El Nino out of what is being implied here with a simple model and based on observations. Okay.